Hello everyone, this is Dr. Vaughn. Going to make a video to show you one of the problems that I've started to work out for section 8.4. This is one of the harder problems, number 34, and hopefully this will be useful to you to see how to work with functions, to find inverses, how to verify using composition of functions that two functions are actually inverses of each other. The question I've selected is one of these rational expressions that can be difficult to work with if you haven't done this kind of a problem before. So the problem statement says to find the inverse of this function and then show it's correct by doing both sets of the composition and showing that they simplify to be just the identity function, which is x. I'll only be doing one of these two, but when you do your homework, if you choose to do one of these kinds of problems for your worked out homework, please do both of these compositions and show it. But you can see these can take a little bit of time to complete. So the first step is to just set y equal to f of x, and basically there's two different ways you can go about this. You can switch the y and the x right away and then solve for y, or you can leave it as is, solve for x, and then switch the x and the y later on. So I'm going to opt for the latter of those two choices. I'm going to leave y and x alone. I'm going to try to solve for x, isolate it, get it by itself. And the problem that you have is that you have two different x's here, one in the numerator and one in the denominator. So you have to do a little bit of maneuvering in order to combine these two different x's to be a single x. If I didn't have this minus 3 and plus 1, I might be able to do some canceling and something else. But I really need to kind of, first of all, separate these two x's and then use addition and subtraction to combine them together in order to factor it out. And we'll walk through each of those different kind of steps. So the first thing I did is just multiply both sides by the denominator here, which is x plus 1, so that I don't have any more rational expressions. Now I have a product over here of y and a binomial, and on the right-hand side I have a linear expression with x. The next thing I'm going to do is distribute the y so that I get yx plus y. So I still have these two different x's, but now they're on two different sides of the equal sign. Now I'm going to subtract the 2x from the right to move it over to the left so that both of the x's are on one side of the equal sign. And I'm going to take all the other stuff and move it over to the other side using addition or subtraction. In this case, subtracting y from both sides. So the 2x gets subtracted over, becomes on the left, and the y gets subtracted over and comes over to the right. Now I have these two different x's, but I can use factoring to combine those two different x's to a single x. I have a single x, and what's left over is this binomial expression that involves the y's instead of the x's. Now I've gone from having two x's and one y to having one x and two y's, which is good, because now I can use division by this binomial y minus 2 to get the x expression by itself. And once I switch the x and the y, this actually is the expression for my inverse function. Now, you might want to turn the size up on your screen if you're watching this on the video. Hopefully this is large enough that you can see it. The next thing we're going to do is now check to see that this actually is the inverse function by putting this as an input into the original function, which was way up here. So everywhere there's an x in this expression, 2x minus 3 and x minus 1, I'm going to replace the x's in the original function with this entire expression, which represents the inverse function. So here's 2 times the inverse function minus 3, and here's the inverse function plus 1. That's the composition of f inverse plugged into f. And now we just go through and simplify this rational expression using the tools and techniques that you practiced back in chapter 7. Alright, so this kind of looks big and ugly. Hopefully you can kind of follow this. This is just writing out what the original problem statement was. The first thing we do is distribute the 2. So 2 times minus x is minus 2x. 2 times minus 3 is minus 6. And for the second expression, which was just a minus 3, I multiplied by x minus 2 over x minus 2 to get the minus is still here. Then I have 3 times x minus 2, which is 3x minus 6 over x minus 2. And you do the same thing. This first term doesn't need simplified, but the second term you just write this as a fraction with the common denominator of x minus 2, which is x minus 2 over x minus 2. Now we combine the numerators. Minus 2x minus 3x gives me minus 5x, and the minus 6 minus a minus 6 is minus 6 plus 6, and that goes away and gives me 0. So I just have a numerator of minus 5x over this combined denominator of x minus 2. And the bottom, what happens is the x's cancel. You get minus x plus x, so that's 0. And then you have minus 3 plus minus 2, which gives me minus 5 over x minus 2. Now you can either invert and multiply, or you can multiply the top and the bottom by this common denominator. of x minus 2, the x minus 2's basically go away, and you have this fraction minus 5x over minus 5. And the last step, of course, is just to cancel the minus 5's and get just the identity function, which is x. So we've shown that the composition of f with f inverse is equal to the identity function. The last step to finish off this problem, which I won't be demonstrating for you in this video, would be to do it the other way around. Show that f plugged into f inverse also reduces to give you the identity function. I hope this has been helpful to you today, and I look forward to your contributions and your comments. I'll see you next time.